Without further ado, let me introduce Tim Frazier. Tim has an undergraduate degree in mechanical engineering from Vanderbilt University and has published papers on eclipsing binary stars. He earned his MFA from the University of Florida and has worked in over a dozen international collections, including the Art Institute of Chicago and the Museum of Modern Art in New York City. In addition to his fine art work, he was the faculty sponsor for a NASA-funded high-altitude balloon project for 6 years, which launched experiments and cameras to altitudes in excess of 90,000 feet. In 2009, he headed a team from Idaho State University that built an experimental capsule which was launched into space by NASA. He is also an avid outdoorsman, a fisherman, a woodworker, telescope maker, and he's the past president of the Magic Valley Astronomical Society. So please welcome Tim Frazier. Thank you.
Well, thank you. I'm always hesitant to speak after that because then you'll realize I'm not really that cool at all. Anyway, I want to thank, first of all, the Haley Public Library for providing services, especially at this time when we're all less mobile. And I want to thank Kristen in particular for walking me through how to use this Zoom technology. Okay. Oh, it says that I'm trying to share a screen, Kristen, and it says that you've disabled screen sharing.
Okay, that's fine. Throw it away.
Was this somebody from here that did it?
Yes.
That's what I thought. I mean, we can try again, but...
So I'm going to mute everyone.
Oh, good.
Okay.
Tim, could I interrupt you for just a second? Okay. And you'll be able to unmute yourself. So for the participants, if you go up to the very top of your screen, you'll see something that says, with your cursor, you'll see something that says View Options. And if you choose the option in the drop-down that says Side-by-Side Mode, then you'll get a real good view of his images. Can you unmute now, Tim?
Okay, yes. Can you
Okay.
hear me now?
Yeah.
Okay. This is a blank screen, and I want to start by saying what we need to see our night sky is indeed a dark sky. And the organization that oversees dark skies is the International Dark Sky Association. It identifies and works to preserve dark sky just as environmental groups work to preserve unique areas of forest or marshland or whatever. They looked around and they found that an area in Idaho has uniquely dark skies. And through work of the Idaho Conservation League, the Central Idaho Dark Sky Reserve was formed. This is a gold tier dark sky reserve, which is their highest tier of darkness. And Central Idaho is the only one of these in the United States. It's also the third largest in the world. This is a map of that dark sky reserve. And you can see it begins around Ketchum and Sun Valley and continues all the way up to Stanley. Now, if you look carefully on this map, which you can get by just going online and searching for Idaho Dark Sky Reserve, if you look on this map, you'll see little gold stars here along the route. These are places that have been identified as particularly easy to observe from. You can pull off the side of the road or walk just a little way and get to a very good observing site. One of the things that makes this dark sky reserve, which is almost 1 million acres in size, so dark is the fact that there are not lights, or they're acceptable lights. And I think one of the things about the unacceptable lights that unfortunately we see a lot of are these unshielded street lights like this. This is the bane of my existence here in Bellevue. Of course, what you want is something more like this. You don't want lights that go out and up. You want the light to go down. And this makes just perfect economic sense too. You don't want to illuminate the bellies of bats and the underside of airplanes. Okay. From a very good dark sky site, what you're able to see on a summer evening, if you look south, is something like this. This is the southern Milky Way. And you can see here this nice long arm of our galaxy here, a dark area, another arm here. In this area, we are actually looking toward the center of our galaxy. This is in the constellation Sagittarius, the Archer. Now, our galaxy is a collection of approximately 300 to 400 billion stars, and it is shaped like this. It took astronomers quite a long time to figure out the shape of our galaxy since we're located inside of it. The problem is one of, for example, being dropped down in the middle of London and looking up and down a few streets and trying to figure out what the city looks like. Okay, in this case, we know our galaxy has 6 spiral arms, and each one is named for a constellation that is in or in that direction of that arm. We see that our sun is located about 2/3 of the way out in our galaxy in what's called the Orion Arm. We can see that's really actually a little side street off of another arm. Okay, let's zoom in and take a look at our solar system. Okay, this really irritates me because they always show our solar system on a poster like this so they can get it all crammed into one area. This is so far off in scale, it's really funny, and I'll show that in just a moment. But it does have all the features of our solar system. We have the sun, and then Mercury, Venus, Earth, Mars, Asteroid Belt, Jupiter, Saturn, Uranus, Neptune, and the minor planet Pluto. And you know, it's never a complete astronomical poster unless you include a comet. Those things are great graphics, I guess. Let's start at the center and look at our sun. Our sun is a gigantic ball of primarily hydrogen gas that is about 800 to 850,000 miles across. Its massive gravity is trying to crush its core. In the center of that core, hydrogen is being pressed together and forming a helium and releasing a huge amount of energy that goes out and balances the gravitational forces wanting to crush it. This is perfectly analogous to blowing up a balloon. The pressure of the air inside the balloon keeps the elastic outside from collapsing onto its center. Now, the sun, of course, beams out a tremendous amount of energy, which is all our source of heat and light. It is also a very stable star, which, of course, we like very much. The first planet out is Mercury. This is Mercury, not the moon. And you can see that it is just a blasted rock. Now, this particular image gives you an idea of how barren it is. It is cooked in the sun's heat, and of course, it has been bombarded by all sorts of debris. The next planet out is Venus. Now, Venus is approximately the size of the Earth, but that's where the similarity ends. The temperature on the surface of Venus is hot enough to melt lead. It is caused by a runaway greenhouse effect. The pressure at the surface of Venus is about the equivalent of being 5 miles under our ocean. It is absolutely crushing. It also rains sulfuric acid. It's not exactly a place we want to visit. Then, of course, there is the Earth. What we're looking at here, of course, is the coast of Africa, and here is Madagascar. Our planet is incredibly fragile. If you were to look at the Earth as if it was the size of your usual globe, which is about a foot in diameter, on that scale, the thickness of our atmosphere would be less than a sheet of paper. As I say, we have an extremely fragile planet. Now, farther out, we run into Mars. Mars is an excellent example of what happens if you don't have an ozone layer. The surface is absolutely scoured by radiation. And we do know Mars at one point had a considerable amount of water, but all that is long gone. The pressure its atmospheric pressure at the surface is about 1,000th of what it is here on Earth. Now we run into the asteroid belt. This is the asteroid Eros, and it's about 5 miles long. It's sort of a warped potato shape. This collection of rocks, and there are billions of them, are in an orbit between Mars and the next planet out, Jupiter. If you watch science fiction movies, you'll see, the Millennium Falcon having to dodge asteroids or things because they're in an asteroid field. Well, this is really not accurate at all. Yes, there are billions of rocks up there, some as small as a small rock, others the size of small planets, but they're thousands, if not tens of thousands of miles apart. So you could literally fly right through the asteroid belt and not see an asteroid. Next up is Jupiter. This is the largest of planets. You could put 1,000 Earths inside of Jupiter. And what we're seeing here in all of these belts, a festooning of gas clouds, because the planet itself spirals on its axis once every 10 hours. This very rapid spinning puts a lot of energy into these incredible storms, the largest of which here is the Great Red Spot. This has been observed for over 300 years. The size of this spot is large enough you could put several Earths inside of it. This rapid spinning also causes something else. The distance from the poles is shorter than the distance across the equator. It is literally spinning itself down into something that more closely resembles a football. The massive gravity of Jupiter is probably what happened to the planet that was forming where the asteroid belt is. It was literally torn apart by Jupiter. This is, of course, Saturn, the ringed planet. Now, the rings of Saturn are comprised of ice crystals and bits of rock and dirt. Although they're thousands of miles across, they're only about 200 yards thick, so it's really a very thin ring. The ring is slowly disappearing. It's raining down on the surface of Saturn. Next out is the planet Uranus, and you can see it too has a ring, a very faint ring. This is debris left over from a moon that was destroyed. Now, I mentioned earlier when you looked at that poster of our solar system that the scale was all off. Let me give you an example of how far it's off using this planet. A few years ago, Pam and I were driving in the bush in Australia, and we knew we were really lost when we stumbled across Uranus. What we had done is driven into the world's largest scale model of the solar system. Now, this model of Uranus is about 6 feet across. At that scale, the distance from this representation of Uranus to the sun would be somewhere around 60 to 65 miles. The last of the major planets is Neptune. Neptune has extreme winds that blow at hundreds of miles an hour. You can see a storm forming here. Neptune is an ice giant. It's about 5 times the size of the Earth. And then at the edge of what's called the inner solar system, we see the minor planet Pluto. When this image was taken by the New Horizons spacecraft, it startled astronomers because they figured it was going to be another burned out rock, sort of like Mercury with nothing but craters on it. But it has formations here. This looks like a gigantic glacier. This is actually solidified gas that is forming this feature here. Now, if we go farther out from Pluto, we run into debris that was left over from the formation of our solar system. All of this you see down in this little depiction are all those planets we've just toured. This sort of donut halo area is called the Kuiper Belt, and this large sphere is known as the Oort cloud. This represents the approximate size of the ball of gas that condensed to form our solar system. The distance from the sun out to the edge of the Oort cloud is approximately 1 light year, or about 6 trillion miles. And once again, of course, we have to have a comet in here for just good graphics. Okay, if we turn our back on our solar system and look out, what we'll see, of course, are the stars of the night sky. Now, in this case, we're looking at the familiar asterism of stars known as the Big Dipper, okay? And if we look at these nearby stars, we see this one up here looks a little peanut shaped. It's actually, with the naked eye and clear night, you can easily see there are 2 stars up there. Let's zoom in and look at those 2 stars with a telescope. And when we do, we realize that the brighter one is actually itself 2 stars. Most stars form in groups, either as pairs or as more, such as in groups that we're going to see in just a moment. In this case, this binary star is easily split into 2 stars with even a small telescope. This is the constellation Vega. All these background stars we see here are in the Milky Way. This bright star is Vega, and we can see the shape of the constellation here, which represents the musical instrument, the lyre. If we look here, we see 2 stars. This is Epsilon Lyra. If I zoom in closer to that with a telescope, what we see is each of those is actually a double star. Again, we see how stars form in multiples. If we look overhead on a summer evening, we'll see the constellation Cygnus, the swan. Here are the wings of the swan, and here's its long neck. And we're going to look at this star right here, known as Albireo. And what we see is a very beautiful double star. This is sometimes referred to as the Cub Scout Star because its colors are those of the Cub Scouts. Now, rather than these 2 stars being gravitationally bound and having formed together, this is a happen chance double. That is, these 2 stars are actually very far apart. They just happen to line up from our point of view. Now, stars also form in clusters. This is a cluster of stars known as M11. The M stands for the French astronomer Charles Messier. Messier was active in the late 18th, early 19th century, and he looked at the sky and mapped out fuzzy spots that he was finding in the sky so that people searching for comets would not confuse these with comets. This particular cluster has approximately 200 stars in it. To give you an idea of how far away this nearby cluster is, if we were to build a scale model of our galaxy, where the distance between the Earth and the Sun was barely the thickness of a human hair, then this nearby cluster would be at a distance of 5 miles. Here we have what's known as the double cluster. Again, we see how these stars have formed in this cluster, these clusters. Now, these clusters, as with that star Albireo, really aren't that close together. One happens to be much closer to us than the other. They just happen to line up from our point of view. Now, besides these open clusters that are aggregates of stars, there are clusters that are much more organized. This is an example of what's called a globular cluster. This is known as M22. It contains approximately 70,000 stars and is at a distance of about 7,600 light years. This cluster is M13 in the constellation Hercules. It contains approximately 500,000 stars. These globular clusters are very old. They're about 10 to 12 billion years old. They formed when our galaxy was first forming and spinning down into its spiral shape. I recently read a paper that said that any stars in a globular cluster like this that had planets wouldn't have them for very long because the nearby stars, their gravity would probably pull them away. Okay. Now, how do these clusters actually form? And the way they form is they start as balls of gas. This is the nebula M8. This is a gigantic collection of gas. The color that you see, the red, indicates that this gas is hydrogen. Nebula like this, called Emission Nebula because they emit light, are excited. That gas is charged up by the stars that are around and in them. This gas then re-emits light that is characteristic of its structure. In other words, hydrogen will glow red. This is exactly like the way a neon sign works. You take an evacuated tube, you put a particular gas in it, you excite it with electricity, and it glows a particular color. This is exactly how this nebula shines. Now, the stars down in here, some of these have been formed out of the gas of this nebula. This is another nebula. This one is M17. It's known as the Swan or Omega Nebula. Again, we can see that it is primarily hydrogen gas that has been excited by the stars in and around it, and it's glowing this color.
Tim, we have a couple of questions.
Okay.
They actually go back to the star part.
Yes.
One question is, why are some stars red and others blue? And a second question is, why do stars form in pairs like you showed in some of those pictures?
Okay. First of all, stars are different colors because they're at different temperatures, different sizes, and your white and blue stars tend to be much hotter than the yellow and red stars. And it depends upon how much mass there was to collapse and form the star. There's a whole series of colors of stars, and of course they're all ranked by astronomers. But that just depends on the size of the ball of gas when they begin to collapse. As far as why stars form pairs, when a ball of gas, such as what you see here, say a little section of this particular nebula, began to collapse, maybe instead of forming just one ball, it began to break up and form 2 or 3 others. There's some evidence to indicate that our star actually formed as a pair, and the other star, as it was forming, was kicked out. And so we ended up in a situation where we could have a stable solar system. Okay.
Well, the sun seems to be a hot topic. You answered one person's question about whether we had a companion star. Someone else was asking, what color is our sun?
Our sun is actually orangey yellow, and that indicates that it's kind of a middle to small size star. As I say, it's very stable, which we like very much. And it will exist in its current form for about another 3 or 4 billion years. I'm going to talk a little bit more about stellar, what happens when stars die in just a moment.
Thank you.
Okay. Well, Swan Nebula, right. Now, this isn't the only type of nebula. Now, this, as I say, is an emission nebula. In this particular nebula, which is called the Trifid, you can see the emission nebula here with the red, with the hydrogen, but all this blue out here is gas that is not excited by stars. It's reflecting the starlight. And since blue light is selectively reflected a little more, we tend to see this part of the nebula as blue. This is called the Trifid Nebula because in early telescopes, they could only see 3 of these lines. Of course, now we can clearly see others here. Now, inside of these nebula, of course, this is where stars form, but stars also age and die. This particular nebula is called the Little Gem. It is actually the outer shell of this star right here. As this star is dying, it's beginning to throw out its outer atmosphere, and that is going out into the interplanetary space, interstellar space rather. Now we can see puffs here of hydrogen, but we can also see other material too. Inside of stars, in addition to taking the hydrogen, crushing them and making a helium, other elements are formed too. Carbon, nitrogen, oxygen, all of the elements up to iron, and including a little bit of iron, are formed inside the nuclear furnaces of normal stars. And this is what's being flung out into space from this star. This is another example of that. This is M27, or the Dumbbell Nebula. Now, this is what we think our star will do as it ages. It will begin to slough off its outer core. It will swell up and become what's known as a red giant star. But, you know, don't cancel your cable service. That won't happen for about 5 billion years. This was originally seen in telescopes as having kind of a dumbbell shape. Of course, with modern telescopes, we can see that it's much more structured than that.
And we have one question. Are all these incredible pictures taken by the Hubble telescope or by a variety of large telescopes?
They're made by a variety of telescopes. What you're looking at right now, an image such as this, or the others of the previous nebulae, the Trifid Nebula or the Omega or whatever, these can be photographed using amateur equipment. Because of the rise of digital astrophotography, it's possible to make amazing photos. One of the things that tends to disappoint people when they look through a telescope and see something like the Dumbbell Nebula is it doesn't look like the photographs. And the reason is the photographs, of course, capture light over a period of time and can show more detail. Also, what happens is that in some of these images, there'll be combinations of not just visible light, but also infrared and ultraviolet. So it'll present an amazing image that it would be impossible for you to see anyway. So some of these are made by professional instruments, but most of them can be made by amateur, large amateur telescopes. Okay, other questions?
Not yet.
Okay.
I'm sure there will be.
Oh, good, good. This nebula that we're looking at is known as M57, or the Ring Nebula. This tiny star in the center, as with those other stars, blew off a shell of its outer gases. But the explosion, rather than being chaotic, was rather symmetrical, so it made this sort of cosmic smoke ring. When you look at this through an amateur telescope, you have almost this perfect sort of donut shape of blue-green gas. Okay. Well, this is what happened.
Excuse me, Tim, I just wanted to remind folks that if you do have questions, just put your cursor at the bottom of your screen. You'll see a little menu pop up. Click on the chat feature. That will appear to you, and you can type your question in the bottom and then just hit enter. So, sorry for interrupting you, Tim.
No, no, that's fine. That's fine. Now, this is how smaller stars, ones the size of our sun or smaller, tend to end their lives. They just poof up and they dispel the gases. They slowly shrink, become a dwarf star, and slowly cool down. Now, other stars that are much larger, when they die violently. This is the supernova remnant. This is known as the Veil Nebula. This is about 8,000 years old. A supernova is when a star literally explodes and it blows itself apart. And of course, what we're seeing here is what's left over from that explosion. Now, what happens in a supernova are two extremely important things. First of all, in that instant of detonation and later as it's expanding, all the elements, iron and heavier, are created. So literally the gold in your jewelry was created inside of a supernova explosion. And this gas that you see here is expanding, and it will go out and become part of the material that will collapse later into another star and possibly solar system. The second thing that supernovas do is they send out a tremendous shock wave. And the shock wave, when it impacts a nebula, can trigger star formation. And so literally in the violent death of this star, it has reseeded the surrounding area with more elements and sent out a shock wave to initiate star formation. Okay. Now, if we look beyond our own galaxy and out, we will see, of course, other galaxies. This is the Great Andromeda Galaxy, M31. It's at a distance of about 2.5 million light years. And you can see, of course, its central core. You can see the spiral arms here. And you see these little dots of red through here and up along here. These are areas of hydrogen gas, these are nebula, where stars are forming. Now, this particular galaxy is gravitationally bound to our galaxy, the Milky Way, and it's headed in our direction, and it will collide with us. But that's going to be a few billion years from now, so let's not, worry about that yet. Okay. Now, there's another nearby galaxy. This is known as M33, or the Pinwheel Galaxy, and we can see in its pinwheel shape and look at all of this hydrogen here. the star formation is going on here. This is about 2.8 million light years away. Now, these three galaxies, the Milky Way, the Great Andromeda, and the Pinwheel here, are all gravitationally bound, and they're sort of our little local club of galaxies. Now, a little farther out are other galaxies that are gravitationally bound with us. This is the two galaxies M81 and M82. We can see that M81 is a very recognizable spiral galaxy with the arms, etc. And over here, M82 is something's going on here. It's called an irregular galaxy, and there's quite a bit of activity going on with it. For some reason, it's literally tearing itself apart. Now, these two galaxies that are about 8.5 million light years away are really part of our local cluster of galaxies. Now, our cluster is also a member of a larger cluster of galaxies that looks like this. Everything in here that is like a fuzzy patch like this are all galaxies. This is in the Virgo cluster of galaxies. These are really quite remarkable. Even with a small telescope, you can see some of these galaxies. And Virgo is just quite frankly littered with them. Now, if we look even farther out, what we end up seeing are superclusters of galaxies. Everything in this frame that does not have these diffraction spikes on it is a galaxy. All of these. Everywhere we look, we see galaxies, more and more of them. It is estimated that if we sum total all of the stars in all of the galaxies that we know of, there are more stars in the sky than there are grains of sand on every beach in the world. I'm sometimes asked at gatherings or at a lecture like this, if I believe there's life elsewhere in the universe. And looking at an image like this, it's hard to imagine there isn't. We know that in our galaxy alone, there are probably several billion planets not unlike Earth at all. If we make the gross assumption that the only way we can have life is like what we have on this planet, nitrogen, oxygen, atmosphere, liquid water, a planet this size, a sun this type, then we're still looking at billions of possibilities within our own galaxy. Now, some people, as they look at an image like this, they say, I'm just overwhelmed. And I say, don't be. Look at this and realize we're part of all of this. This is part of what we are and where we are in the universe. And I think it certainly deserves celebration. Okay. Are there other questions I can answer?
There aren't any in the chat box right this minute, but I think people were so focused on what you had to say and these astonishing images. So let's give them a little bit of time to type a question in. But I have a question.
Sure.
So when we look at the image of Saturn and its
Okay.
beautiful rings, was that once a moon or several moons, or what actually caused those rings?
Well, the rings themselves are crushed material from moons. It was believed there was a couple of larger moons. They possibly collided and formed the basis for the rings. Now, we know down inside, for example, in this area right here, Cassini's division, and some of these other little divisions here, they're separate because they're tiny moons in here. They're actual moons. Saturn itself has almost 80 moons, I believe. Now, some of these are just captured asteroids, but certainly that's what's the material is. All this ground up dust and ice. It is being replenished from some of these small moons, but it seems to be falling inward at a higher rate than it's being replaced.
We do have a question now about Jupiter and its 10-hour rotation. Why is it only 10 hours, and do all planets rotate? What causes them to rotate, and do they all rotate in the same direction? That's kind of a string of questions, sorry.
Wow, that's a lot. Okay.
I made some of those up myself.
Okay. Well, let me say, yes, all planets rotate. And that's a consequence of as they form in and the material begins to accrete and form a planet, something large enough that it will become spherical. The conservation of angular momentum says they have to spin. Yes, they all rotate. No, they don't all rotate in the same direction. I'm going to jump here to out to Uranus again. Uranus was hit early on, knocked over on its side. So rather than having its axis of rotation, say, maybe perpendicular to its orbital plane, it's laying down and pointing almost toward the sun. It also rotates in the opposite direction. It got smacked hard early on. As far as Jupiter, it is primarily a gas giant with a solid core. That solid core may be really a very dense hydrogen gas that is acting like a metal. It's so dense. But its rapid rotation is something, I honestly, I'm not sure why it rotates that rapidly. But I do know that energy through the Coriolis forces are what helps make these spiral festoons that we see in these bands of gas.
I'll stick with planet questions. We have a question, but our moon does not rotate and it's a sphere. So how did that happen?
Our moon actually does rotate. It just rotates once every 28 days. This is why we see the same face of the moon toward us. If the moon didn't rotate, we would see all sides of it. Okay, so this is not unusual. This sort of synchronizing of the orbital period with the rotational period does happen more often than you might imagine. Anyway, we have an unusual face of the moon toward us. You know, if you look at the face of the moon, you see those dark areas in it. What were known as seas. The ancients thought this was actually water. Well, now that we know what the other side of the moon looks like, it's all pockmarked with craters and all torn up. It doesn't look like the face toward us at all. When the moon first formed, and it was torn from the Earth with something about the size of Mars smacked into Earth, a side-swiping blow early on, and it tore out a big chunk and that formed the moon. The moon was very close to the Earth. It established this synchronous rotation very early on. And one face, of course, was always toward the Earth. The Earth was very, very hot, and it melted a lot of the moon. And that's why we think we have this more smooth-looking surface toward us and a more cratered one away from us.
You mentioned earlier that suns often form in pairs. Do planets form in pairs that kind of rotate that kind of way? I mean, I think about the Earth and the moon are sort of almost like two planets because the moon's pretty big.
Actually, if you were coming in from space and saw the Earth and the moon, you would think it would be a dual planet because the moon is so large with respect to the size of the planet it orbits. The problem with that is if you have a couple of planets and they're trying to rotate around each other, they're also rotating around the sun. And this tends to set up forces that really don't like that very much. And so one of the planets tends to get kicked out or destroyed. Early on, Jupiter kind of wreaked havoc with part of our solar system. And as I mentioned, it tore up the what's now the asteroid belt. Planets can probably form as pairs, but they're not going to last. And stars, of course, as they form in binary pairs, it's very difficult to form a stable orbit around two objects. You run into that awful three-body problem that makes mathematicians pull their hair out. And so usually what happens is we have a single star that has planets, or you have a binary or multiple star system.
So when we say that we see planets around other stars,
Right.
are we seeing solar systems, so multiple planets
Yes.
around other stars like we have?
That is correct. Initially, we could only see the biggest planets, ones that were the size of Jupiter or bigger. I mean, because they were easier to pick out using a variety of different methods. But now, as we're becoming more and more and more refined, and we have better instruments, we're beginning to detect smaller and smaller planets. In fact, we're beginning to find ones now that are about the size of the Earth. Our instruments are getting good enough that when a planet revolving around another star goes in front of that star, it's possible to look at just the edge of that planet and get an idea of what's in its atmosphere. Right now, this is pretty primitive, but they've seen oxygen and water, for instance, in the atmospheres of exoplanets. When the Webb Space Telescope will be launched, it was scheduled to be launched a couple of years ago. It's been postponed, but once it gets in orbit and is set up, it will be powerful enough to literally begin to see gross features on exoplanets. And with that instrument, we're going to be able to tell a lot more about the planets. Right now, we know of about 5,000 planets revolving around other stars.
Wow, that's amazing. And then we have a question, and you may understand this better than I, so I'll just ask it. Are the blue streaks gravitational lenses?
Yes, they can be. They are. Actually, I think there were some in that one. Let me jump to that image here. This looks like one right here.
Is that what you're thinking about, Chris? Is that your question? And you can unmute yourself, I think.
The answer is yes. That looks like a gravitational lens to me too.
Yes.
There looks like there's some in the upper left too. There looks this one just past the big white star, just to the left of it, kind of northwest, right there. That looks like a gravitational lens to me.
Yeah. Now, what he's talking about is
Thanks, Chris.
Yeah.
You're welcome.
What he's talking about is that massive objects bend light. This is one of the things about that Einstein and his general relativity demonstrated. And if a very far distant object is, say, directly behind a very massive object, its light will be bent around that object, sometimes going out in streaks, other times creating multiple images of a single object. There's a very famous photograph of 4 objects almost symmetrically placed around a 5th one, but there are only really 2 objects. One was way behind a nearer massive object, and it bent the light 4 ways around it, so you saw 4 images of it.
Oh.
It really is a remarkable phenomenon. Okay.
We have a question now. Can double stars have planets and actually support solar systems?
At this point, I don't think so, for the simple reason that the two stars revolving around each other, it would be almost impossible to establish a stable orbit around one of those stars. The one scenario where that could happen is if the two double stars are far enough from the planet that gravitationally the planet sees them as a single star, and it can form an orbit around both of them. As I say, you're wandering into this three-body problem, which is quite a mathematical quagmire.
Well, I don't see any questions quite yet. Let's see. Thank you for showing that image. How do we find out about the shape of our own galaxy if we're standing in the forest?
Okay, let me go back to it here, and well, first of all, we can view out and see other examples of galaxies. And so, you could say, well, maybe we're like that. Well, but if we were like that, this would have to happen, so we can't be like that. So there was somewhat of a process of elimination. There was also a process of using other than visible light to look out, in particular radio, because all of this material out here, when it gets excited, would emit radio waves. For example, neutral hydrogen emits radio waves at a 21 centimeter wavelength. And so by tuning in and listening to that and pointing in a particular direction of the sky, you can go, oh, look, there's a lot of hydrogen there, or whatever. So in other words, using other means besides visible, we've discerned this. Now, specifically, how this barred spiral shape was determined, rather than just a pure spiral, and how many arms there are, etc. Again, I am not sure how everything was mapped. Okay. Other questions?
Not right now. Any questions from anyone dying to know about why Mercury looks like that, or how come Pluto was so beautiful and we never knew it, or anything about the asteroid belt or the outer planets, anything about those beautiful nebula?
The thing about the
Tim, can you see questions that have been sent to you on chat privately?
not right now, not the way I'm set up. No, I can't, Ted.
Okay, I entered two. Can I ask them to you now verbally?
Sure.
Okay, my first question was, if the moon faces us the same side all the time, does that imply that the moon actually has an unsymmetrical density?
Not necessarily, although there are gravitational anomalies that have been seen by orbiting spacecraft that are mapping the moon, in particular Clementine. There are gravitational anomalies. Oh, gee, it's a little more dense here or whatever. But no, overall, I think the density is fairly constant. The thing about synchronizing orbits, and I'm not sure of the mathematics behind that, but as I say, that happens between objects that orbit each other. For the longest time, it was thought that Mercury was that way, that it had synchronized where one face only was facing the sun. But now they realize it orbits, there's a 2 to 3 resonance there between them. To answer your question about the density, I don't think so, but I can't say for sure. How's that for a non-answer?
I had one other question, if I can still ask
Sure.
it, I'm going to do two. One was, do you have an idea of the ratio of open space to matter in the universe as we know it?
I am not sure. And the reason is the more I'm reading, the more I realize that empty space is not so empty. Now, you have one atom per cubic centimeter is not very much, but it's something out there. The fact that the matter has clumped the way that it has, that the galaxies and the clusters and superclusters are not symmetrical. They're not evenly distributed. Lends credence to the fact that the Big Bang was a very asymmetrical or a very chaotic event, and things were thrown out in various directions rather than symmetrically from a core outward.
Thank you.
That gave people time to think up some good questions for you, Tim.
Okay.
So why does Sagittarius A star,
Right.
parenthesis, all galaxies, spin into the poles? And that's a question from Brent Bostwick, and he may need to have more of a conversation with you about that. So why does the Sagittarius A star spin into the poles?
Okay. Sagittarius A, that's, of course, in the direction of the center of our galaxy. And we're talking about a supermassive black hole at the center of our galaxy. And as matter falls into it, some of it is radiated out along its magnetic force lines, along its magnetic poles. We see this much more violently in other galaxies, where they literally throw out jets of material that are moving at relativistic speeds that are thousands of light years long. Now, why that's going on in our galaxy, what's going on with Sagittarius A, I honestly can't give you a solid answer on that. That's as far as I can go.
Great, thank you. We have someone finds double stars very interesting. How do we know that they're actually double and it's not just one star sitting behind another star?
Well, they rotate around each other. And the period of those orbits can be hundreds or thousands of years, but it's possible, because astronomers are very patient, to plot the orbits of stars. A photograph would be made, say, 1890 on a glass plate, and then it was compared to one made in 1968 by a undergraduate astronomy student like me. And we would sit down with the two plates and we would look at the star and say, oh, look, this one moved just a little bit around it. And we would measure that movement. Also, there are ways of looking at stars with a spectroscope. That is, break the light of the stars down into its component colors. And by studying that, there can be shifts within those colors that indicate there's movement. And so we don't have to wait necessarily that long. We say, yeah, this one's moving, and because all of these colors are shifted toward the blue end of the spectrum, we know it's coming toward us, as opposed to red end of the spectrum, it'd be moving away from us.
So we'll have two more questions. One is, I think it was Rigel in Orion was dimming markedly recently in the last year, but now it seems to be back to its kind of glorious self. Could you talk a little bit about that? Yes,
and that was, I think you mean Betelgeuse.
Maybe, okay, Betelgeuse. Thank you.
Yeah, and Betelgeuse is a star that is dying. And from all indications, when it goes, it's going to be a supernova. I mean, it has the mass to do that. And what we're seeing now are fluctuations as it's kind of revving itself up to explode. And it'll go through a period of brightness and it'll get brighter and then it will dim again. And it'll do this over and over. But looking at that star and other stars and supernova that have just happened, we know this one's getting ready to pop. Now, when I say that, it could be thousands of years from now, because cosmically, that's the blink of an eye. But what we're seeing is inherent instability in that star.
Thank you. And then our last question is an exceptionally deep question. Could you talk a little bit about black holes and what we know about them now?
Okay. A black hole is a supermassive object. One way they are created is in a supernova. If the star is of sufficient size and the blast is of sufficient power, it literally compresses the core of the star and makes it so dense that not even light can escape. In order to leave the Earth, you have to exceed a particular speed, or the gravity of the Earth will just pull you back in. This is called the escape velocity. The greater the mass of a planet or any object, the greater the escape velocity. It would take, you would have to go at some 300,000 to 400,000 miles an hour to escape from the gravity of Jupiter. To escape from a black hole, well, you can't, because its escape velocity is greater than that of light. Now, what this means is it sucks everything around it in, and it creates a accretion disk of material that is spinning around it. And although we can't see a black hole, we can see its effect on the surrounding space. And this accretion disk, which is comprised of whatever material is unfortunate enough to get too close, is like a gigantic whirlpool that is slowly being sucked into the black hole. And as that material gets closer and closer to what's called the event horizon, and once it passes that, there's no coming back. And as it gets closer and closer, it gets more and more energetic. And just before it cascades over, they begin to emit gamma rays. And so we can look for gamma rays, and this is one of the clues of a black hole. Now, what is on the other end of a black hole? And we honestly don't know. There are all sorts of mathematical theories about what happens to something that falls into a black hole. Does it come out somewhere else in the universe? Does it come out somewhere else in time? I mean, we honestly are not sure. We also know that for whatever reason, all galaxies seem to have a supermassive black hole in its center. And by supermassive, I mean it's not one that's comprised of, say, 10 or 20 solar masses. It's one that's millions or hundreds of millions of solar masses. And why this is, we're not real sure. Does the black hole form first in the galaxy? Is the black hole part of the galaxy's formation? They're not real sure at this point. We also know that now we can listen to black holes. And this is because of an amazing experiment that's set up in Hanford, Washington. There's another one that's in Italy, and there's a third one that's being built somewhere else. I think it's Japan. And when black holes merge, it is so violent that it literally sends out gravitational waves. It really, in other words, shakes the very fundamental material of which the space around us is comprised. And with this very sensitive instrument, we're able to detect that. And now, with a couple of these things online, we're able to get a direction in space of where this is coming from, so we can look at it. From the size of these, you can think of them as seismic vibrations, we're able to get an idea of the size of the black holes that have merged. and how much energy has been released. Black holes are really a rather fascinating topic. And of course, it's not a good sci-fi movie unless they don't throw in a black hole somewhere. You know, they have to do that. But okay, I hope that answers the question.
I think it was an excellent, excellent answer. So I know we started late. Thanks everybody for your patience, and I know we've run longer than we were originally intending. Tim, do you want to take more questions? Do you want to just wrap it up? How are you?
Well, I'm fine with time. If people need to sign off, I certainly understand. But if there are more questions, I'll certainly be happy to answer a couple more.
Okay. There's one from John Archer, and I'll just read it. It says,
Okay.
it seems so incredible that our moon should happen to have a rotation that always shows the same side to Earth. The chances of such a rotation speed just happening must be huge. Isn't there some scientific explanation explaining a rotational speed being so perfectly coordinated with Earth's?
Oh, yes, there is. As I say, this synchronizing of the rotational, the rotational timing with the orbital timing of going around something, we see that in other solar systems. We see it in other objects. So it is not uncommon. And it's a consequence of basically gravity working on the two objects. At one point I understood the math, but it eludes me now.
And then we have a question, with so much debris in space, for example, the Kuiper Belt, how is it we can see the light of a tiny star so far away? It seems like the light would get blocked or shielded or bent from our perspective.
Okay. The thing is, yes, there's a lot of stuff out there, but yes, it's very spread out. And so it's, you could go into the Kuiper Belt and you'd be in the middle of it, and it would be, still the vacuum of space, and it would be possible to see through it. I say that, and I've also know the astronomer down at the Harrod Center at CSI, Chris Anderson. And part of what he does in his research is he looks at asteroids and wants to refine their orbits. And the way you do that is by you know pretty much what the orbit is, and you look at where it's going to be in the sky, and you say, oh, look, it looks like it's going to pass in front of this star. And so you watch that star, and if its light dims, and of course you measure the dimming and how long that took, you can get a lot of information and help refine the orbit of asteroids. I'm saying this because, yes, all this debris can get in the way of starlight, but it's a pretty darn rare occurrence. And if you really want to see something get in the way of starlight, when's the next solar eclipse? You can always go and see that. But no, there is a lot of material out there, but it is so spread out, we can easily see through it.
So a question along that same line, we hear from time to time about some object hurtling towards us, and sometimes we know it might be coming our way in a few weeks or months, and sometimes it seems like it's just days away, and it passes by. Something recently passed by, not quite dangerously close, but remarkably close. So that stuff's just out there hurtling around and isn't rotating around something, or is it, what's happening there?
Yes, there's a lot of material out there, and there are asteroids and other objects whose orbit around the sun, everything in this solar system orbits around the sun, and its orbit will cross ours. And, we don't want to be there when that happens. Okay. And so we are very carefully plotting the orbits of these near-Earth asteroids and comets. Remember, every time you see a meteor in the sky, that's a piece of debris that is passing, that, you know, the Earth sucked in with its gravity. Every time you see a meteor shower, we're passing through the material left behind, probably by a comet, but possibly an asteroid. And so, yes, we're colliding with that all the time, but it burns up in our atmosphere. What we're worried about is the one that doesn't. And to that end, right now, NASA's conducting an experiment way out on the other side of our solar system, where it is trying to move an asteroid out of its orbit to see what methods it could use should we decide one is really going to hit us. What can we do? And so we want to have like a good plan of action to do that. But again, you know, it's the distances and the space involved. Our solar system alone is a gigantic space. And so a lot of stuff, billions and billions of chunks of rock are out there floating around, and they're orbiting the sun. But for one to hit us, fortunately, most of that occurred in the formation of our solar system. And Jupiter, thank heavens, has swept a lot of that up because of its large gravity, and has swept a good portion of the inner solar system clean of that. Doesn't mean it won't happen, and it will happen again. But hopefully we're going to be prepared for it. And I was just going to say that in 1908, over in a very desolate section of Siberia, there was an asteroid that came in and exploded and flattened 800 square miles of timber. If that had happened over a major city, the disaster would have been unprecedented. So yes, it happens.
One last question, and I just wanted to let you know too that as people are leaving, they're saying very nice things in the chat and how much they enjoyed it, and looking forward to your next talk. But what's happening with the Hubble Space Telescope? Is it? I mean, it's been up there a long time. Are we still getting good quality pictures from it? What's the lifespan?
Well, the life has been extended a couple of times. Because, you know, sooner or later its orbit will degrade and it'll be sucked back to Earth and burn up. But a couple of times they've gone and basically rejuvenated it. They've added new experiments, new power packs, etc., to keep it going. And, you know, the Hubble Space Telescope is not that big a telescope. Compared to some of our ground-based telescopes, it's rather small. It's just got a really good dark sky that it takes advantage of. And of course, being above our atmosphere, it doesn't have to deal with that. But it's still going strong. And there are all indications that they will keep it going for at least the next 5 years. When the Webb Space Telescope gets in orbit, its mirror, that is the part of it that collects the light, is many, many times the size of the Hubble Space Telescope. So it will be able to see much dimmer objects and be able to give us much more detail.
Well, I don't think anything could hold a candle to the awe that Hubble introduced us to with those incredible pictures of nebula and galaxies. And I mean, I think it spawned hundreds or thousands of astronomers or astronomer wannabes. So.
Oh, absolutely. Yeah, it's an amazing instrument.
Thank you very, very much, Tim. I felt like we really grilled you tonight. And
no,
it was just delightful. So thanks everybody, and have a wonderful evening.
All right. Thank you all very much. I appreciate it.